Hi, good afternoon. This is acids, bases, and their reactions. And so we're going to start off talking about tonight's lecture with an acid. And we're going to give you a very, very, very general definition of an acid, and then we're going to modify this definition as we go down the road in AP Chemistry. But for now, we're just going to say that an acid is a something that will ionize. So ionize in solution, an aqueous solution. It's something that's going to give off hydrogen ions into solutions. Now, obviously, we're going to modify this later on down the road, but this will suffice for our definition right now. And so let's break this idea up of an acid that ionizes in aqueous solutions to form a hydrogen into two different categories. And the first one we're going to call a strong acid. And this is going to be an acid that does ionize in solution to give off hydrogen ions, but it's going to do so completely, meaning 100% of the hydrogen ions that are present will be given off. Now, when you have strong acids, one of the things that we need to make sure we do is when we write we're going to write these guys as ions if they're in a net ionic equation. And let me give you an example of what that looks like. So if we were to take hydrogen chloride gas and bubble it through water, what would happen is it would make hydrochloric acid. Hydrochloric acid is a strong acid, so then we would ionize that into the hydrogen ion, which would be aqueous. And then we ionize that into the chloride ion, which would be aqueous as well. And we wouldn't need to write water because it is aqueous and we're good. And so we have ions. Now, for all intents and purposes, in AP Chemistry, there are going to be 7 strong acids that we encounter, and anytime we encounter one of these 7, we have to make sure we ionize it in an ionic equation. So these are the strongs, and you need to know them. We have HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. So you're going to need to know these, and you're going to need to know the names of them as well. And so HCl is hydrochloric acid, hydrobromic acid, hydroiodic acid for HI. HNO3 is called nitric acid. H2SO4 is sulfuric acid. HClO, perchloric acid. And then you have chloric acid. And so those are 7. These are 7 that you've got to commit to memorize to memory as being 7 strong acids. And you'll see on our next test, there's just going to be a question that says, what are the 7 strong acids, and what are their formulas, and you'll have to write them. So commit them to memory because we're going to use them very, 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 very often. So with that said, we should also talk about another category of our acids, and these are the weak acidic solutions. And so these guys are going to be an acid, usually starting with a hydrogen. So you have H, sometimes we call it HX, something like that. And X can represent a whole host of things from a single atom like a fluorine to a polyatomic like an acetate ion. But these guys are going to not ionize 100% of the time. They might ionize 10% of the time. So in a solution, you might have 10% of the molecules ionized into hydrogens and their negative ion, where 90% stay together. Okay, so these guys don't ionize. And so they still do release a hydrogen, though. They can cause pH to drop. But we do not ionize these guys in net ionics. And the best way to know if you, or how to figure out if you have a weak acid, if you're not a strong acid, which is one of the 7 strongs I talked about before, you're automatically weak. Okay? And so that's how you know. Now, give you a couple examples of some of these weak. A real common one is acetic acid, which is that hydrogen stuck on the front of an acetate ion, or HF, which is hydrofluoric. Now, hydrofluoric, as we'll find out later, is super, super, super reactive and actually very, very dangerous. But it does not ionize 100% of the time, so we cannot classify it as a strong. Okay, so now we're going to talk about strong bases. And a strong base, and we're going to give you a definition of a base that's also a very general definition. It's not the exact definition, and we'll modify it later. But these are going to be things that are going to have 100% ionization of a hydroxide ion, that OH ion. And these are guys that we're also going to, we're going to ionize in net ionic equations. And our strong bases, we also have a list of strong bases, although it's really, really easy to memorize. To be a strong base, you are an alkali metal plus a hydroxide. So anybody who is something like lithium hydroxide, sodium hydroxide, potassium hydroxide, those are all our strongs. And our Cassarba. And we have to remember that when we do have these Cassarba hydroxides, there is going to be 2 hydroxides ionized per 1 mole of calcium hydroxide. Just keep that in mind, and that'll come up later. Just like our weak acidic solutions, our weak basic solutions are pretty easy to identify. If you're not one of the strong bases, you're automatically one of the weak bases. And so all other bases, usually those are our beryllium and magnesium hydroxide plus any other metal hydroxide, like let's say iron 3 hydroxide or zinc hydroxide or something like that. We do not ionize in solution. And as we learned the other day, these guys are going to be typically insoluble. They're not going to ionize anyway. So that just covers that. Next idea I want to talk about is the idea of a neutralization reaction. Now, neutralization reactions are going to follow the following pattern, which is basically you're going to take an acid, and you're going to react it with a base. It's going to form a salt, and it's also going to form water. And it typically follows along with a double replacement reaction, although not necessarily always, but usually. Okay? And so let's give you an example of what a neutralization reaction would look like, and then we'll kind of talk about how it all goes through here. So we might get a problem that looks like something like this. So we have a 0.5 molar solution of hydrobromic acid being mixed with equal volume of a 0.5 molar potassium hydroxide solution. So let's kind of go through this. So we have hydrobromic acid first, and we'll write a complete equation to start out with before we do our net ionic. And so we have HBr as our acid And then we have potassium hydroxide, which is going to be KOH. And in just looking at this reaction, it takes the form metal, non-metal, metal, non-metal, and we have a double replacement reaction, very similar to our precipitation reaction we talked about yesterday. So let's just switch these guys. So we're going to take the potassium, put them in the bromine. We'll call that KBr. And then we will take the H and go with the H, and we'll go HOH, which hopefully you can recognize HOH being the same as H2O. They're the same thing. Okay? Now, the two reactants, here we have a strong acid. It's one of the 7 strongs. Here we have a strong base, one of the strong bases, an alkali plus a hydroxide. Here we have a soluble salt. I know this guy's soluble because it's got an alkali metal in it. And here we have a pure water, because it's water, a pure liquid, I mean. Now that's important for what we're going to do next, which is we're going to ionize. Now, I'm going to ionize everybody right now, and then we'll go net ionic at the end. And so strong acids always get ionized, so we're going to have our hydrogen plus our bromine. Strong bases get ionized. Potassium plus our hydroxide. Salts. This salt has potassium in it, so it is soluble. And then we have water, which we're going to leave together. Now, there's our complete ionic equation, and now let's do our net ionic equation based off of this. And so I can cancel out my spectators, bromine here and bromine here, or bromide, I'm sorry. Our spectator ions, we can cancel them out. We have the potassium ion here and the potassium ion there. Also spectators, cancel them out. And so what we're left is the hydrogen ion plus the hydroxide ion yields H2O. And what this says is, and the reason why they call it a neutralization reaction is because hydrogen ions cause pH to drop, hydroxide ions cause pH to rise, and if you have equal numbers of these, you get a pH of 7, which is neutral, thus the name neutralization reaction. I'll throw just one more at us just to show you how we can give you a curveball on these types of things. And so let's do another example. Okay, and so what we have here is we have solid potassium hydroxide being added to a 0.1 molar solution of acetic acid. So let's do the complete first, and then we're going to talk about what's going on here for the net ionic. So for the complete, I have solid potassium hydroxide, which is KOH, solid, and we have acetic acid, which is HC2H3O2. And again, this is going to take the form of a double replacement reaction where we're going to have these two switch places. And so we're going to get a potassium acetate plus water being formed, HOH. Now, this is an aqueous solution, and this one is going to be an aqueous solution because we have an alkali metal, plus we have the acetate ion, which is also soluble. Now, here comes the trick for the net ionic, for our ionize. The first off is we're looking at a strong base here in potassium hydroxide, but because this is a solid, we cannot ionize it according to the rules of who do we ionize, because we don't ionize solids, liquids, or solids, gases, or pure liquids. And we should also add to that, we don't ionize weak acids or weak bases as well. So we're going to leave that guy together. We look over here and we have an aqueous solution, but this is a weak acid. And we do not ionize weak acid, so we're not going to ionize it. We come over here to the other side. We have potassium acetate, which is a solution. Potassium is in it, and so is acetate. And this guy we do ionize because